Hi, good evening, everyone.
Good evening.
Good evening, sir.
Good evening.
Good evening, sir.
Hi, Manjunath.
Okay. Hi.
Hi.
Yes.
We'll wait for, I think, yeah, it's not time yet. I think 2 more minutes we will wait.
Yeah, sure. Yeah, let's wait till 6:01 and then start.
Okay, sure. Yeah.
It's 6 o'clock.
Shall we start, Shobhan?
Yes, I think we can start.
Let me share.
Yeah.
Okay, so welcome everyone. So this is the third lecture. So yeah, I was not very clear what to do because it's not sure. So I'm clear about one thing. So the last lecture, which is tomorrow for me, I will spend entirely on spectral theorem of symmetric matrices. It's a very important theorem, but often not emphasized enough. It's the most important maybe in thing you learn in linear algebra. But so that's what I was planning. So today I was planning to maybe spend a little time on generalities of vector spaces and various associated spaces and so on. So that was what my plan was. Before doing that, so there was something I remembered actually. I mean, so the other day, some of you asked me for references and so on. Actually, I mentioned some. There are many good books in linear algebra, but there is a very fun book which some of you may like. I had forgotten about it. when I went back and looked at it, I saw that in fact the Fibonacci thing that I did is the first example there. So let me give you the, yeah. So maybe in the chat I will put this. I will put the. So where is the chat? Chat. So I put it in chat. Maybe I will also write in the OneNote so that people who come later will also be able to see. So this is just a side thing. So this is a book by Matuchek. There is some accents on this, which is called something like 33 miniatures in linear algebra or something like that. It's a lot of fun. It is not something where you learn linear algebra systematically. That's not what this book is for. Okay, you don't get to learn linear algebra systematically here. What it has is 33 applications, like I was doing in the first lecture, something which has probably nothing to do with linear algebra, but some combinatorial problems, some other geometry problems, some things. Okay, so which and how linear algebra helps to solve that. Okay, so that's the thing. So there are a lot of interesting things. You don't have to read it in any order. You can read any of the in any order. So it is you will find a PDF online somewhere, legally or illegally. You can download and read. Okay, so now let me come to what I was doing. So last time I was talking about vector spaces, right? So what did we talk about? We just talked about some examples of vector spaces and basis and so on. So one of the things is, yeah, so we talked, every vector space has a basis. So in the tutorial, I had given some question about how to asking about if I give you V and W. Okay, so let's recall this statement that I mentioned last time, which you know very well. Every vector space has a basis and all bases have the same cardinality. Okay, that could be also infinity. But if the so finite dimensional, so we will stick to finite dimensional vector spaces. So this common cardinality is called the dimension. So finite dimensional vector spaces means when dimension is finite, right? So in the tutorials, I had asked some questions of the following kind. So suppose I give you two vector spaces. V is, let us say, yeah, so 2 cross 4 real matrices. And W is, let us say, R to the 8. Are they isomorphic or not? This means, are they isomorphic or not? What is your answer to this? You have done such problems, right? Anyone?
Yes, sir. It is also isomorphic.
They are isomorphic. How do you say?
They have the same dimension.
Okay, very good. So it is one of the interesting points. I mean, so the thing is, it looks very trivial, but you realize that this is actually so helpful when you don't have it, right? So like happens in life, you realize the value of things when you don't have them. So this is true. So if V and W have the same dimension, then V and W are isomorphic. How do you prove such a thing? So you take a basis here. Take a basis, maybe V1 up to Vn. Then here you take a basis, W1 up to Wn. Okay. And once you have that, we are assuming the dimensions are same. So it's the same n in both cases. So then what do? How do you define an isomorphism?
We take an element of V.
Yeah.
That will be the linear combination of elements of Vi's.
Okay.
So X is equal to summation alpha is Vi's for alpha is in F. And we
Okay.
define T like T of summation alpha I Vi is equal to summation alpha I Wi.
Right. Okay. That's correct. So you define L from V to W by defining, you send, let's say, L of Vi to Wi. Vi goes to Wi and extend linearly. And extend linearly, right? That's what you meant. So this way, any two vector spaces with the same dimension are isomorphic. Of course, the opposite is also definitely true. If dimension V is not equal to dimension W, then V and W are not isomorphic. Of course, any two isomorphic vector spaces will have all the same properties. So if they don't have the same dimension, they certainly are not going to be isomorphic. You see, this is a simple point, but something to keep in mind. You don't, it is somehow, you're lucky to have this. This doesn't happen in other algebraic structures. Like I mentioned, other algebraic structures, think of groups. So if you have two groups and you want to check whether they're isomorphic, it is very difficult actually. So you can't just say that they have the same size. Okay, both groups have 10 elements, so they are isomorphic. That's not true. There are many different groups, possibly of some of the same, for some cardinalities, maybe there is only one, but in general, there are many groups for a given cardinality. So you don't have this kind of an easy check. So this is one of the things about vector spaces. It's just too easy that if the dimensions are same, then they are isomorphic. Isomorphic, as I said, it means they are the same, but there is a point to it. So this is one of the, this is an abstract point, but something that took me many years to appreciate, that isomorphism in some sense means they are the same vector space, but isomorphisms are all not natural. So one of my confusions when I studied linear algebra at first is, finally, when you have this, that means if, so in particular, if dimension V is n, then V is isomorphic to Rn, or V is isomorphic to Cn, depending on which field you are of scalars you are using. Okay. So if you are using a real field, it's isomorphic to Rn, it's otherwise you are isomorphic to Cn. So my confusion when I was learning linear algebra was, then if all vector spaces are basically Rn and Cn, why don't we just say Rn and Cn, and instead of giving all these abstract definitions of vector spaces, what is the point even? Why should we do that? Can you say why? So if everything is isomorphic to some Rn or Cn, why not just define that? In fact, I would suggest that if you are having trouble with linear algebra, you just think vector spaces are Rn and Cn, learn it, and then come back to this point. But I assume many of you have gone beyond that point. So why this abstract definition of vector space and all that? Why should we care? Why can't we just say Rn, Cn?
Because there exist other examples which occur naturally.
But everything is isomorphic to Rn, right? Some Rn, some.
Yes.
What are the other examples you have? Finite dimensional. If we stick to finite dimensions, everything is isomorphic to either Rn or to Cn. So why do we care? Why should we even bother?
Maybe due to the presence of a lot of bases.
Exactly. So the thing is, basis exists, but there is no natural basis. That is the point. Okay. So that's the difference between an abstract vector space of n dimensions and Rn. What is the difference between an abstract vector space V of dimension n does not come with a basis. Okay, it comes with many bases. It doesn't come with a particular basis. So to identify it with Rn, you have to make a choice first. On this side, we have to choose basis on both sides. Right, on both sides we have to choose basis. To identify means to get an isomorphism. That's what I mean. To get an isomorphism, because once you have an isomorphism, they are basically the same. You can work on either side and transfer results from one side to the other side. But we must choose basis. On Rn side, it is kind of clear that we can choose the coordinate basis, E1, E2, En. Right? That is natural. That's why Rn comes with a natural basis. But an abstract vector space, there is no natural basis. So I may choose one basis and get an isomorphism like this. You may choose a different basis and get a different isomorphism. So then we cannot transfer results. What my calculation show, your calculation show, they will not show the same things. Ultimately, the results are same, but the vector space itself doesn't come with a natural basis. Okay, so that is the real issue. That's why this abstract viewpoint is actually kind of important. So let me tell that point in a slightly different way. I don't know if this made any sense or not. If you have any questions, as always, unmute yourself, ask. Please do that at all times. Any questions? Okay. So if no questions, let me say why this happens. I mean, so let's give an example. Okay. So let me show it by example. So you can even start with R3. Let's start with R3. Okay, Rn I have written. Okay, let's leave it as Rn. Now I want to consider, let's look at the set of all vectors in Rn such that the coordinates are, sum of coordinates is 0. This is a kind of thing one might do many times. What is it you know about W? This is a subset of V, but what more?
Subspace.
It is a subspace of V. Okay. So I am now introducing this word, I mean, which you already know, subspace of V, meaning that it is a vector space in its own right. So this just means that if X and Y belong to W and alpha and beta belong to the scalar field, then alpha X plus beta Y belongs to W. So whenever you find a subspace, you find a subset of a vector space which is closed under scalar multiplication and addition, that means it becomes a vector space in its own right. So it's a W is a vector space in its own right. Right? What is its dimension?
n-1.
Its dimension is n-1. How do you know?
Because one vector is depends upon other. Vn or v1 is can be written in the linear combination of other.
Okay, that is you are right. But can we just go back to the definition of dimension as the cardinality of a basis?
Number of vector.
So then you are saying that the dimension of W is n-1. It is correct, of course.
And sir, we can think of this thing as geometrically as well.
Sure. It is a, if you are in R3, it's a good idea. So if you are in R2, if n is 2, then what is this set of things? It is all those for which x plus y is 0.
Yes. So this is a straight line. Passing
X minus 1 minus 1.
Yeah. So W will be this. So V is the whole plane. So here in this example, V is the whole plane. And this thing is W. W is whatever the points lying on this line are W. A three-dimensional picture, okay, I am not good at drawing, so but let me make a small attempt.
So the number of equalities that we get in such equations restricts the degree of freedom. So
Right.
That's why degree reduces by that many equations.
Okay, so we'll come to that. But here what happens is this is a plane. I mean, okay, this is a horrible picture which nobody can understand, but this is a plane passing through the origin, but it is kind of, it is, okay, I can't write it. You can, actually, it's not a bad idea, by the way. Something reminds me, since you are teachers and you also want to know how to, I mean, visualization is a very important part of mathematics. So if you know how to use computers a little bit, that will be very good. Actually, there are a lot of free software to do a lot of basic mathematics. All of basic mathematics you can do. I mean, there are paid software like MATLAB Mathematica, which are very expensive, and it may not be possible for colleges to buy them. But there are many free software also available. With that, you can visualize a lot of things, and that gives you a good idea. So rather than seeing a badly written diagram like this, you can see that. Anyway, let's come back to this question. How do we say that dimension? Without using intuitive ideas are very important, but just from the fact that the basis has to have n-1 cardinality. For that, you have to find a basis, right? So here is an example. Even if my big space is the nice space, which is Rn, okay? When I go to subspaces, there is no natural basis. You see, here itself there is a problem. Even if you only are interested in Rn, it does not, W does not come with any natural basis. So that's why this abstract viewpoint of vector space is important, because even if you are working in Rn, subspaces of Rn are not, it's not obvious how you identify it with Rn-1. In other words, what is the basis you choose? That's not clear. So here are one example. One example of a basis is I can choose 1, -1, 0, 0. So let's take n equal to 4, just for definiteness. This one, 1, 0, -1,
0,
0, 1, 0, 0, -1. This is a basis. This is one basis. Here is a completely different basis. Okay, what else should I put? I think this is a basis. Anyway, you can see that there is nothing natural about any of these things. Why I should pick one or another? Even this kind, I can pick many others, right? I mean, I can make it 0, 0, 1, -1, 0, 1, 0, -1, or 1, 0, 0, -1. In what way is this basis better than this basis? There's nothing to choose. So that's why abstract viewpoint is kind of important in many of these.
Excuse me, sir. This is 9, but actually, I have one more suggestion. Using rank nullity theorem, also we can say dimension is n-1.
That's correct.
the observation is the set whatever you have mentioned is nothing but the null space of the matrix 1 by n matrix whose all
That's
entries
true.
are 1.
You can view this as this subspace. Shortly we'll talk about linear transformations maybe. This is actually, if you already, anyway we are not making a very systematic survey of the whole subject. So this you can also think in another way as the kernel of a linear transformation. Okay, so what is the linear transformation from where to where?
Rn to R.
Okay, so you define a linear transformation Rn to R, both are vector spaces. You define L as L of V1 up to Vn, V1 plus up to Vn. So this is a linear transformation, that is clear. And it's if you look at the kernel of this linear transformation, which by definition is all those vectors for which LV is 0. It is exactly the W that I got. W is all those V for which this V1 plus up to Vn is 0. And what is the range of L? Is this an onto transformation?
Yes.
It is, right? So if I want some number X, how can I get it in the image? You can look at X comma 0, 0, 0. If you look at the vector X comma 0, 0, 0, L of that will give you X. So every number X comes as the image. So range of this is R. So, and what you are saying is the rank nullity. This is an illustration of the rank nullity theorem. That dimension of W, which is n minus 1, plus dimension of R, which is 1. This is, by the way, W is the kernel of L, and this is the range of L, will give you the dimension of the underlying space, which is n. So n minus 1 plus n. So it is an illustration of the rank nullity theorem. But to keep things clear, this is not a place where we can go over systematically. One of the things you should do when you do read mathematics is to keep the logical part of it also. The intuitive part is very important, but the logical part also should be clear. So what follows what? Okay. So rank nullity theorem comes only after you understand what is even the statement of rank nullity theorem comes only after you know the notion of dimension. Otherwise, you cannot make sense of it. You have to know the notion of dimension. You have to know what is the meaning of kernel and range. You have to know that they are subspaces. And then you have a statement that their dimensions add up to the dimension of the domain space. So you have to have all that. Okay, so the logical part is important, but that's kind of not possible to go over things systematically in a short course like this. So we'll just make a tool. This is a kind of chaotic tool, that's all. Anyway, but so this is the kernel. So what is R? In this sense, so this space W is the kernel, this is range. But in terms of the original vector space, what is this? Do you know? Maybe the question is too vague. So let's look at now. So subspaces are one concept that we touched here. Okay, subspaces there, and then let's look at L from V to W. Okay, so kernel L is the set of X in V such that Lx is 0. And range of L, we know what it is. It is all Lx, X in V. We just look at. So this is a subspace of W. So this is a subspace of V. So do you know what is range of L? I mean, in other words, is there some identification of range of L with something in V? not in V, but something else you construct. I'm just asking for a keyword, not a meaningful math question that I'm asking here.
Column space.
No, I'm not asking in terms of L. For V, what are vector spaces associated to a space? So suppose I have a vector space V. So what I'm talking about here is from one vector space, there are many vector spaces which come. For example, you can take many subspaces. A vector space has many subspaces. How else can you get some other vector space out of a vector space V? What are the other vector spaces associated close to it?
Quotient.
Quotient. Okay. That's the keyword, quotient space. So this range is actually, in fact, it can be identified as the quotient space V mod W. That's how we write it. So let's recall, what is quotient space? What's the definition of quotient space? So if V is a vector space and W is a subspace, so what is the quotient space? As a set, what is it actually? So have you seen this?
Sets of
V plus W.
V plus W. Comma V plus W is
For
also
all
there.
V belongs in V.
It is the set of all
V plus
X plus Y such that
plus W
for all
X belongs to V.
X belongs to V. So, but it's a little confusing. So what is, so let's draw a picture. What it means is the following. Suppose you have a subspace here, which let's write like this. Maybe this is my subspace. So this is W, okay? So what happens is that, see, this is R2. So the big space is R2. And in that we have a subspace which is isomorphic to R1. Now the point is you can take translates of W. Okay, so if you take translate W, you will get another line. It does not pass through the origin. So you can draw many translates of W on the other side. If you can translate parallelly to itself, you get many other things. These are called affine subspaces, but if you haven't seen the word, don't even worry. So the translates of W, these are different W plus X. Actually, W plus X can be the same for many different X. Okay, so if I translate, so for example, let us say this point is, okay. So anyway, now let me just say, so this is the collection where you don't write again. So the point to note is, can have X plus W equal to Y plus W if X minus Y belongs to W, right? In fact, if and only if, that's if and only if. So this collection has a vector space structure. So these lines themselves can be thought of as one line. Instead of thinking of all these lines, each line, if I identify as a point, okay, then it looks like that itself forms a space or vector space. This picture is very misleading because this one looks like it is another subspace of V. It's not exactly a subspace of V. It is a, that's a very, it should not be thought of as a subspace of V. It has a vector space structure where you define X plus W plus Y plus W is same as X plus Y plus W, etc. Okay, so this is called a quotient space. An alternate way to think about quotient space, which is a very important important thing. So this is one way of thinking. Just define it like this. So a second way, which is very much the same, but I will just say it in another way. On V, define an equivalence relation. If x minus y belongs to W. So you identify, so in other words, all these points. So the thing is, if you take any 2 points in one of these lines, say I take 2 points here, their difference, what did I say? Right, so their difference is actually belongs to W. Their difference, so if this is x and this is y, then x minus y belongs to W. That is how these things are. So you define, so this is a check that this is an equivalence relationship. So you probably know the definition of equivalence relationship. It has to have certain properties, transitivity, symmetry, reflexivity. So, so whenever you have an equivalence relationship, so the equivalence classes are precisely this x plus W. So these are precisely the equivalence classes under this equivalence relation, and they have a vector space structure. That's what the quotient space is. Okay. The third way to think about the same thing is just this: take any linear transformation from V to W, V to some other space V dash, such that the kernel of L is W. Okay. Then the range of L can be identified with the quotient space. Okay. So this is the thing that I was saying here. So these are three ways to think about it. You can think of quotient space as made up of this collection, but here is a more abstract way to start that. You define an equivalence relation where you don't want to differentiate vectors which are in W. Equivalence relationship means that they are not equal, but you want to think of them as equal. For practical purposes, sometimes we regard them as equal. So x and y we regard as equivalent if the difference belongs to W. Then the equivalence classes are the distinct ones, okay, really distinct ones. And they have this vector space structure, which is called a quotient space. Similarly, the another way to think is anytime you have a transformation, then the range of that, if the kernel is W, the range can be thought of as the quotient space. There is a natural way to identify this. So these are different ways to think of the quotient space. Okay. Any questions, comments about quotient space? I don't know if you use quotient space as much when you teach linear algebra or not. Okay, so all right, so that is one other space. Subspace is one, quotient space is another one, which we just went over. Okay, what else is there? Any other vector space associated? Once you have V, is there any other vector space you know about? So have you heard of dual spaces?
Yes, sir.
Okay, so dual space of a vector space. That is also very important. So if V is a vector space, what is its dual? Sometimes denoted V star, sometimes denoted V dash. What is it?
The set of all linear functionals on V.
It is the set of all linear functionals from V. Functionals means they are linear transformations into the scalar field or the one-dimensional vector space. Okay, is that a vector space? It itself has a vector space structure where we can add L1 plus L2 is the transformation which pointwise addition. Alpha L is the linear transformation which maps V to alpha times L of like this. So this is a vector space in itself. What is its dimension? So let's say dimension V is n.
And the same as dimension of V.
So the same as. Okay, so why is that? Does anyone know?
Dimension of V.
Huh? Sorry, somebody answered something. I could not hear. Why is the dimension n?
So actually it is dimension of V into dimension of the field, which is 1.
Okay, so you are saying some more general fact, but why is the dimension of how many linear functionals are there? So one way to see that the dimension is n is, so what is the meaning of dimension? So let u1, u2, un be a basis here.
So we can use the fact that for any basis and for any set of n elements in the range space, if T is a suppose linear mapping from V1 to V2 with dimension of V1 is equal to n, then for any set of n vectors in V2, we can have
we don't know dimension of V star is n. We are trying to show dimension of V star is n. So I am saying that let's start from scratch. Suppose V is a vector space with dimension n. That means it has a basis, right? Of size n. Now produce for me n linearly independent linear functionals. Then we will know that dimension of V star is at least n. Right? So have you seen this construction? So let's define L1 like this. L1 of ui will be 1 if I is 1 and 0 if I is greater than or equal to 2. Okay? That is, and extend linearly. So this is a linear functional because you are extending it. L1 of u1 is 1. L1 of u2, u3, un will be 0. Then define L2. How do you define L2? I want a new linear functional. Can you define?
the second element is going to 0 and all other elements are going to 1.
Okay. 1 if I equal to 2. That is L2 of u2 will be 1. L2 of the others will be 0. And so on, we define Ln. And then extend linearly. So it is an exercise, or it is there in text or read. Okay, it's not an exercise you have to do yourself. You can try to do yourself. If you don't remember, if you forget a proof, if it's often nice because then you can try to prove it yourself. So L1, L2, Ln is a basis for V star. Okay. So V and V star are in that sense isomorphic. But again, here is the cautionary thing. But there is no natural isomorphism. Okay. So there is no natural isomorphism. That is the problem. So what about if you take, so it is a strange thing that if you take V star star, it is the dual of V star. Do you know what that is? I mean, I mean, you have a vector space. For vector space, I can associate its dual. You can associate a double dual. So it happens that, so why I mentioned this is that, of course, this also is, what will be the dimension of this? What will be the dimension of that?
Same as V.
Yeah. So
Same as V.
because the dimension of the dual is dimension of V star, and dimension of V star is dimension of V. So this also will be N. So V star star is also isomorphic to V. But it is an unusual point. It's an important and unusual point that, however, here the isomorphism is natural.
Can you clarify why it is natural here and not natural there? I'm not able to get that point.
Yeah. So that is the strange thing. So what is V star star? Okay. So how do you define V star star? The point is for every, so here is how you identify V star star with V. So I'll just write V double star. Okay, that means V star, then star. Okay, what is the isomorphism between V and V? So define for any x in V. Define, I need to find some m of x, okay, in V star star. Okay, by the following. What is an element of V star star? So instead of writing m of x, just because it looks it will look confusing in a moment. So let me write m sub x. Okay, that is okay, I hope. So let's define m sub x in V star star. But what is an element of V star star? If I have to define an element, what do I have to do? What is an element of V double star? What is the definition of V double star?
Functionals from V star to R.
Right.
Vector.
So it is something. What is it? So mx is a function on V star, right? It should be a. So mx is a linear functional on V star. That means it should be a functional from V star to R, right? Mx in V star star means that is an mx.
No, sir.
Huh? The linear functional mx from V star to R. And how do I define? I have to define for any L. And I will define it as L of x. See, I start with an x in V. Now I want a linear functional on V star. So to every L, I will send it to the number L of x. L is in V star, so L of x is a number, right? So this is the identification. So this identification, x going to mx from V to V star double star is an isomorphism. This is maybe a subtle point, but you see why it's natural, because I didn't choose any basis to define this. Did I say, let me choose a basis in V? No, I did not. I did this isomorphism without choosing a basis. That's why it is natural. Okay, so this is maybe, if this is not clear that it's an isomorphism, this is again various things I write as exercise. Well, I don't have to write, because anything we don't understand in math is an exercise. Okay, and of course, except open problems, they are not exercises, which nobody knows. But anything that we don't understand, that itself is an exercise, trying to understand that. I have already defined for you the mapping. It is up to you to show that it is an isomorphism. More confusing than all that. Actually, proving that is not going to be difficult. Confusing is where these things are, what are these objects. It's very confusing. And if this confuses you, do not at all worry. You will get used to it. For example, to think of a collection of functions as a vector space. Okay, each element of V star is a function on V, but we think of them as an element of V star. This idea of thinking of functions on some space as points of another space is actually quite abstract, and it takes some time to get used to. V star star is even more complicated. You have a collection of functions on V, and then you have collections of functions on this. V star star is that. So in the beginning, the difficulty is in wrapping your head around this kind of stuff. At least I found it that way when I was done. Any questions, comments? Then I will move to another topic. I have about 10 minutes. I'll talk about something further. Is this okay? I mean, if you don't see that it is an isomorphism, so the point is for X, I have defined Mx. Okay, first of all, you should check that Mx is a linear functional. Is Mx an element of, what is Mx of alpha L1 plus beta L2? By definition, it is alpha L1 plus beta L2 of X, which means it is alpha times L1 of X plus beta times L2 of X, which is same as, what is L1 of X? It is Mx of L1, right? That's the definition of Mx of L1 plus beta times Mx of L2. So Mx does belong to V star star is what this shows. The rest of it I will leave to you. So X going to Mx is an element of V star star because of this. But now you have to check that the mapping from X to Mx is an isomorphism. It should be linear, and then it should map, it should be injective and bijective. Okay.
Sir, where do we use this dual functions or dual linearity? Applications of this?
Well, you get them all the time. So like they are the simplest linear transformations if you want. Okay, so the linear transformations, linear functionals are the simplest linear transformations that are there on a vector space. Yeah, so they are measurements. I mean, so how shall I say it? So let's look at, for example, Rn. So if you look at Rn, so if I send x1, x2 to, let's take R2, R3, x1, x2, x3 to anything like 2x1 minus x2 plus 3x3. This is a linear functional. Okay, so one way to think of it as measurement. I mean, it is you have a vector and it is a linear measurement of it. Okay, measurement means so in real life, X may denote something. It may denote an image. It may denote something. Okay, it may denote some complicated object. So, for example, a photograph can be thought of as a vector. Well, each pixel is a coordinate, and at each pixel we have a number which shows how dark or light it is. Let's say it's a black and white photograph. Then it is made up of pixels, which are tiny dots. And what is a photograph? A photograph is at each point, it tells you how dark or light it should be. So there is a number here which tells you how dark or how light this dot should be, and another number to tell how dark or how light this number is, etc. Okay. So a measurement of a, so how do you, I mean, you can store this whole data, but you can also store linear combinations of it. So for example, if these vectors are, so this entire image can be coded in a computer as maybe there are 10 to the 6 pixels, 1 million pixel. I mean, it's not uncommon. 1 megapixel is not uncommon at all. So a photograph is a vector of length 10 to the 6. And then you make some measurements of it. Okay. So for example, x1 minus x2, x1 plus x2 plus x3, x37 minus x44. They may not have any meaning, but each of them is a measurement. These are measurements. And each of them is a linear measurement. So those are what linear functionals are. Sorry, I don't have a very good answer to your question. So I blabbered this and that. I don't know if it conveyed anything. So each linear functional should be thought of as a measurement of the underlying object, which is a vector. Okay, so
Okay.
sorry, I don't have a very good answer. Okay, if I think of a better answer, I'll tell you next lecture.
Okay.
Okay, so let's do something. Let's talk about a little bit about projections. So okay, so I'll rather now I have how many? Oh, I have a few minutes. So okay, so let me talk about projections. So now let's take V is R2 for example, and you take two subspaces. Or rather, maybe since I don't have time, let me not talk about projections in general. Let me come to inner product spaces. Okay. So let me talk about inner product spaces. So let V be a inner product space. Let's assume that the dimension of V is n. Okay. So just continuing on the kind of things I was telling. So what is V star? So it turns out that in inner product spaces, there is a natural isomorphism between V and V star. So in general, I told you that the dual and the vector space, there is no natural isomorphism. If I give you an element and give me a linear functional associated to that, there is no such thing. You can do it after you choose a basis. But in inner product spaces, that is one of the very special properties of inner product spaces, that there is a natural isomorphism. How is that? So let's define a mapping. Okay, how do I define a linear functional on V? So I want to give a mapping from V to V star. For every X, I will associate a linear functional Lx. Okay, can you tell me how a vector X can define a linear functional? You have to use the inner product.
Inner product of X comma V for every V in V.
Very good. So Lx of V you define as inner product of V with X. Let's put X in the second coordinate just. Okay. So this becomes a linear functional. This is linear. So because of properties of inner product, show that Lx is an element of V star, because inner product is linear in the first variable. Lx of V1 plus V2 will be Lx of V1 plus Lx of V2, etc. But this is in fact an isomorphism. Okay. This is in fact an isomorphism. Again, I will leave it as exercise. Exercise means read, possibly read. There's a isomorphism between V and V star. Okay. So only in inner product spaces there is a natural way to identify the this with the dual. That is an interesting point actually. What I'm saying may not make too much sense actually. It didn't make sense to me when I read this for the first time. But in mathematics, sometimes you understand things, sometimes you just get used to things. Okay, so when you get used to it sufficiently, you feel that you have understood it. Okay, so that also happens. But in inner products, there's another, so some other special constructions in inner products. So I will have to carry over part of this to the next lecture. This will naturally continue, and the whole business of spectral theorem will come naturally. It is something related to inner products, you can say. But just in a minute or two, I will just say something about a special construction. So let V be an inner product space, let W be a subspace. What can you do to W that you cannot do in a general situation? Okay, a very vague question, just asking for a keyword. So if I have a subspace, so let's say dimension D, dimension W is, let us say, P, which is less than N. So then we can associate another subspace of dimension N minus P. What is that?
Orthogonal.
Orthogonal complement. It is called W perp V in the vector space such that V inner product W is 0 for all W in the given subspace. Okay. You take all those vectors which are orthogonal to everything in your space. So for example, in the very simple case of R2 with the usual inner product, if your subspace is this, then you take all vectors which are orthogonal to this, you get a perpendicular line.
It's 7 o'clock.
That's another subspace. So this will be W perp. Okay. So this W perp is a subspace, and not only is it a subspace, it is a, so what is it about W perp? Let me state it and then maybe I will continue from here. Right. 1. W perp is a subspace of V. 2. Dimension of W perp is exactly N minus P. What is the most important point here?
W perp.
We can discuss direction of V, W and W.
So the W direct sum W perp is V. What this means is every vector V in the vector space can be written in a unique way as X plus Y with X coming from W and Y coming from W perp. Okay. So for example, if I have a vector here, I can write it as the sum of this. So if this is my V, this will be X. This will be Y and this will be X. So those are the projections of, this is called the projection of V to W, and this is the projection of V to W perp, the orthogonal. This is called the orthogonal complement. Okay, so next lecture I will continue from here and then go on to the spectral theorem for symmetric matrices that is very intimately connected to this orthonormality and inner product business. Okay. Sorry for going over time. I'll stop now. Oh, sorry. Yes. Yeah. I stop now. So you can stop the recording if you like. Now, if there are any questions, I'll stay for a few minutes, but also feel free to take a break before the next lecture.
Yeah, we will start at 7:10, and if anyone has any questions or anything to ask, feel free to ask now.
Hello, sir.
Yes.
Can you? There was this question last time about why restricting to R or C for the definition of an inner product, right? And you said positivity plays a role there.
Yes, that's
but then we can at least include Q or some fields like which are subfields of R, right? And what avoids us from including?
Yeah, no, you are right. Over Q, it makes sense. Positivity makes sense.
Or in some sense, completeness is helpful for,
Yeah, it's a good question. I have never seen it being used. It's a no, you have a point. Of course, Q is a place where positive makes perfect sense. And if you have a vector space over Q, you can certainly talk about an inner product, perfectly valid. Yeah, you are right. Actually, I haven't ever used them, but it seems valid. I don't see why not.
Okay.
So the natural now here is a perspective that is that this vector spaces, there are many different mathematicians will have very different perspectives. So people like me who are more from the analysis side, for us the vector spaces are really real and complex vector spaces. That's what we care about. Okay. But if you look at algebra, like Venkatesh, who is going to give the next set of lectures, for them, most of the time the vector spaces they encounter with over some fields which are not R or C. It will be some other fields, could be finite fields, could be field extensions of rational numbers, could be some periodic fields, all sorts of things which to us are exotic. To them, that is the more natural one. So in number theory, all the time they work with field extensions of rational numbers. So your question is very valid. Maybe there are good contexts where that inner product will be useful there. I'll have to think about it or look up. Okay.
Thanks.
Okay. So so for those who came late, let me just again reiterate because this is too nice a thing to miss. I put it in chat, but I mentioned this other book. Oh, where did it go? Okay, sorry, here. Oh, okay, I didn't even come to the new page. Okay, there's this book I mentioned, which is quite a beautiful book. It's not for learning linear algebra systematically, but it has a lot of interesting, fun applications of linear algebra, like the one I gave on Fibonacci numbers and many others to combinatorics and other problems. So which are very nice actually. So you can look at that.
Sir, I have a question regarding the cardinalities, if allowed.
Regarding the?
Cardinality of sets.
Okay. Oh, cardinality of sets. Okay.
Yes. So, as regarding the subsets of real numbers, which are infinite, they are either countable or uncountable, right?
Yeah, okay. Let's say that.
Rational numbers are countable.
Yes.
Real numbers are uncountable.
Yes.
And as far as irrational numbers are concerned, they are also uncountable. So my question is, does there exist an explicit bijection from the set of real numbers to the set of irrational numbers.
Yeah, that is possible, I think. I do not, yeah, explicit means it should be possible to do it from all real numbers to I cannot give you one off the top of my head, but somebody may have worked out one. Usually it is not needed for anything that is there, but your question is certainly valid. You can ask, can you give me one explicit one? I would have to think. I never, I think there probably somebody has worked out something. So because yeah, perhaps. The thing is, you can identify real numbers with sequences. Let's say in binary, so a number x can be identified with its binary expansion. That means is x and xn is 0 or 1. But sometimes there are ambiguities. Some numbers have multiple binary expansions. You have to choose one. So yeah, so you may want to, so if you want to try this, so the rational numbers are ones that correspond to a particular type of this ones, right? So yeah, the overall answer is I don't know off the top of my head, but there might be one.
Okay, sir. Thank you, sir.
So since you asked that question, let me before leaving mention one fun thing. So there are natural numbers and there are real numbers. So suppose I have a subset A of real numbers, and let's say it is infinite. So is it one of two things? A has the same cardinality as natural numbers, or A has the same cardinality as real numbers? So this is a question.
Continue hypothesis perhaps.
Yeah. So the thing is, it's a very interesting question, which is, I mean, you can say it is true, you can say it is false, it doesn't matter. You cannot, I mean, it depends on, in some precise sense, you can say it is neither true nor false. Anyway, my time is up, so Kosuhik will be here, so I'll stop sharing and then.
Yeah, I just want to make I mean, it's not a mathematical question. I think it was very comforting to hear from my experienced teacher that sometimes it takes time to get used to things and then we feel that we have understood it, because I think at times we push ourselves too hard to understand and we feel bad that we are not understanding it quick enough. So it was nice to hear from you that yes, there are certain things which takes times to get used to it.
Oh, everything takes time.
Yeah. So I think Kosuhik is here. We can.
I think, sir, this is first said by Newman. Am I audible, sir?
Yes. Yeah. Yes.
I said it was perhaps first time said by Newman, who said that in mathematics we do not basically understand things; we get used to them.
Okay. Okay. One Newman. Okay. Should we start then? It's time. I think it's 7:11.
Let me share my screen.
Okay. Sure.
Okay, can you see my screen?
Yes, sir.
Yes, sir. We can see.
Okay, so yeah, today's lecture I plan to cover a bit of Cauchy sequences and series. Hopefully, tomorrow's lecture, the last one for this week, that will might be on continuity, I guess. Yeah, let's see. Okay, so just a reminder what we did last time. So last time we started with sequences. We did a few results on convergent sequences. When is a sequence convergent and so on. And then we saw one important example, which was monotone. If you have a monotone sequence, either increasing or decreasing, if it's bounded, it's always it converges. In particular, the limit is the supremum for increasing or the other one. Okay, and then we saw this nice theorem that any sequence has a monotone subsequence. This was a nice idea of Polya, which we used, that there are either these peak points that we defined, and using the fact that there may be either infinitely many peaks or finitely many peaks, we showed that this is true, that either there is always a increasing subsequence or a decreasing subsequence. And finally, we ended with Bolzano-Weierstrass theorem, where one of the ways we could show this was simply take a bounded sequence. You just apply the previous theorem. You extract one monotone subsequence. That monotone subsequence, first it's monotone, but it's also bounded because the original sequence is bounded. Therefore, you can, what we proved earlier, you can say that this subsequence has a limit. And therefore, we said, I didn't finish the whole loop here, but we had some order in which we went. We started with order completeness of real numbers. Then we could prove nested interval. And then we could also show monotone convergence that follows from order completeness. From monotone convergence, we went to Bolzano-Weierstrass. I've drawn some of the other arrows here, but you should try some of these. It's good to kind of, so I may not cover much more of this in these lectures. Okay, so yeah, so let me start with Cauchy sequence and series. And again, feel free to ask any questions if there at any point you don't feel comfortable with something, or you have some other suggestion or something. Okay, so maybe I start with just recalling definition of a Cauchy sequence. Recall a sequence xn. We always deal with real sequence. Xn is a Cauchy sequence if so you want to say somehow that so what is the motivation for a Cauchy sequence, at least in the real line? So I mean, if you know that yesterday you did problems where you were asked to compute limits of certain things. So if you knew, or if you guessed that this is the limit, then you can try and prove that you take the difference and you estimate it and so on. But sometimes it's not, you just want to know that the sequence converges. You don't really care about what the limit is. That may not be your goal. But if you just want to know that it converges and you don't know where it converges to, then this is a useful tool to have. Just estimate the difference of this for large enough n. So let me just recall. Xn is a Cauchy sequence if given epsilon positive, there exists an n again which depends on epsilon, such that the modulus of xn minus xm is less than epsilon for all n and M bigger than or equal to capital. Okay. So Cauchy sequence means that for each error, you can find a large enough index n so that after that index, all the points xn and xm, no matter how large they are, all of them, their difference in absolute value is at most epsilon. Okay. So of course, when we say this, then anytime we make a new definition, you want to know examples. What are such sequences? What are not? What is an example of a sequence that is not Cauchy, and so on. But so let us just do a few examples. Some of these I will not prove, but yeah. So anyway, so definition is okay. Again, just see the order in which if you give me an error, I can find a large enough natural number for which this is true. Okay. Okay. So examples. Okay, this is our main example. Essentially, there is only one example that we. Okay. So, if xn is a convergent sequence, then it is Cauchy. Right? If xn is convergent, how does let's not write it down, but maybe just orally we can convince ourselves. How does one quickly show that convergent sequences are Cauchy? So remember, convergence means that there is a limit L, and all the numbers, all xn after some stage, they lie between. Say, if you give me an error epsilon, they lie between L minus epsilon and L plus epsilon. So from here, how can we conclude that it is Cauchy? Any
for a given epsilon, if and if it's convergent to L, then for a given epsilon we can find a capital N which is close to which is close to L. So if you use simple algebra, then we can show that which is also close to xn and xm also.
Yeah, what is the main thing there? What is the one important? That's just one line. What is the important thing there?
What is the limit you were talking about?
Xn is convergent, then let's suppose L is the limit of Xn.
Yeah.
So we can apply the epsilon definition there. We can say that mod of Xn minus L is less than epsilon by 2. And then we can start with the mod of Xn minus Xm there. And then we add and subtract L there.
Okay.
So that way, so on this side, we will have epsilon by 2 plus epsilon by 2.
Yeah, if you give epsilon, you find n large enough so that the limit definition limit holds, and then you use triangle inequality with so you start with epsilon by 2, for instance, and then use triangle inequality is the main thing. Once you know xn minus L is small, then xn minus xm is less than xn minus L plus xm minus L in modulus. So that is the main thing. Okay.
Yes, so we will add and subtract limit L.
Yeah.
Mod of xn minus xm is equal to xn minus L plus L minus xm. Then mod of A plus B is less than equal to mod A plus mod B.
Exactly.
So we will write mod of xn minus L plus mod of xm minus L. And then both are less than epsilon by 2 plus epsilon by 2. That is equal to epsilon. Yeah.
Yeah, good. Yeah, that's what that's the strategy. Yeah, thanks.
That's what I said, I guess.
Yes, yes, we all agree. Yes, that there was everyone gave the right answer. Okay, so let's move on to yeah. So any convergent sequence is Cauchy. So obviously there is a question waiting there. So if I take a Cauchy sequence, does it have to be convergent? Okay. So of course this depends on the space where you are in. So, but before that, let me also just write a few facts about Cauchy sequences. Facts. or maybe let me just write for no fact because I don't know how many I have. So if xn is Cauchy, then it is bounded. So we are collecting various properties of this Cauchy sequences. So with this definition, we saw that one example to keep in mind that all convergent sequences are Cauchy. But nevertheless, we have take any Cauchy sequence, then before answering whether it is convergent or not, maybe we can try to answer a weaker one. Do we know it is bounded? Because we know that every convergent sequence is bounded. So maybe we can start with this, then it is bounded, right? Why is this? Okay, so maybe I do this one. So let's say that there exists some n such that xn minus xm is less than 1 for all n and m bigger than or equal to capital N, right? So I have taken epsilon to be 1 here. So if epsilon is 1, I find a corresponding natural number capital N for which this is true. In particular, since this holds for all n and m bigger than or equal to capital N, it holds for m equal to capital N. So we can write xn minus x capital N less than 1 for n bigger than or equal to capital N, right? Is that okay? So if you so if you just look at the size of xn in absolute value, then we can apply triangle inequality. Which is less than 1 plus mod x capital N. So if you call this your, so maybe we call whatever. This, remember that x capital N is a fixed element of the sequence. So it's not changing with so little n, for all little n bigger than capital N, you are bounding it by 1 plus mod x capital N. Okay. So therefore, if you want to show boundedness of the sequence, so you want an m so that mod xn is less than m for all n. This is the meaning of a bounded sequence. So what you have achieved here, this is for n capital bigger than or equal to capital N. So you have achieved some bound for all large enough numbers. So you just have to estimate the remaining finitely many numbers, x1, x2 up to xn capital N minus 1. So that way you can just take, so we can take m to be the maximum of the finitely many things. So mod x1, mod x2 and so on up to mod xn minus 1, and then you also include this 1 plus mod xn. Okay, so there are these first n minus 1 elements taken in absolute value, and then the last one is 1 plus mod xn, which we did in the previous slide. Okay, so if you take the maximum of this, so for all n bigger than capital N, you have this bound, and the first n minus 1, you take the maximum. So this way we can show it is bounded. Okay, so any Cauchy sequence is bounded. Is this okay?
Yes, sir.
Okay, so just to kind of verify which is so maybe not a Cauchy sequence, or let's say that suppose, let me ask a question. So what does it mean here? It means that here we are saying that the terms xn minus xm for large enough indices, they all become small for large n, right? So suppose I instead just say, suppose I simply know that we only know let me just write here. Suppose we know that this goes to 0 as n goes to infinity. Then can we say that xn is Cauchy? Okay, so notice what I'm doing here. Here we had mod xn minus xm, all large enough n, right? So suppose I know for n large, I'm taking just consecutive differences, xn plus 1 minus xn. Suppose I know that it goes to 0, then can we say that this sequence must be a Cauchy sequence? What do you think? Any ideas? Am I audible?
Yes, yes, it is Cauchy only.
Yeah.
We can use the same triangle inequality and then prove this.
So you think it is true? Xn, this is Cauchy?
Yes, yes, it is Cauchy only. Yeah.
Okay, sometimes I'm not able to hear.
Yes, it is Cauchy only.
It's true. Okay, someone says okay. So Pooja and other Sudhir Kumar also says it's true. Okay, does anyone say it's not true? Who says it's not true? Maybe everyone says yes, or some of you say no.
I'm not sure actually. I mean,
okay.
I'm trying to find an example. So
Yeah.
can we get such example?
Okay, but how does one approach? If you want to say it is Cauchy, okay, maybe we can try some initial approach. How will you try it? So you want to say, suppose I give epsilon.
We can try using triangle inequality. We can prove that.
That is the most natural approach one would take. So if you give epsilon is given, I want to somehow estimate this, right? Xn minus xm. Can I make it smaller than epsilon? Okay, let's say n and m for large enough n and m. So of course let's say, suppose just for definiteness, let's take n bigger than m. Okay, how will you try it? If you want to estimate, the only way that we know is triangle inequality. So maybe you will add and subtract. So maybe let us do triangle inequality. You will write this as xn minus 1 plus xn minus 1 minus xn minus 2 all the way up to xm plus 1 minus xn, right? This is okay. I just added and subtracted xn minus 1, xn minus 2, blah, 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 all the way to xm plus 1. Okay. So, I mean, we know that maybe each of the terms goes to 0 when these indices are large. But does that mean that if you sum up, will that necessarily have to be, if each of the terms is small, but does that mean that when you sum up, then maybe something can go wrong, or maybe it still works okay?
It's finite, so it will.
Okay. So xn equal to root n. Yeah. So yeah, that's the point. So how will you, if at all you look for an example or a counter example, how should you look? Maybe this is one approach one can take, that you want something that successive differences are going to 0, but not the sum of these many ones. Okay, so there are many examples. So this is actually, so the answer to this question is not necessary, that it is not, you can find sequences which have this property, but it need not be Cauchy. So I think it was, let me just check, it was I think anomaly, right? Yeah. So yeah, you can take several ones. Let's say that maybe if you take xn to be so anomalous example, xn is root n. Okay. You can take, there are several ones. So if xn is root n, maybe xn is log n, and so on. Okay, so if you take root n, for instance, root n plus 1 minus root n. So why does this go to 0? Because you can write this as 1 over square root n plus 1 plus root n, right?
Yes. That goes to 0.
Yeah, so we have seen in the previous problem sessions and so on that this goes to 0. Similarly here, this is xn. So this is okay. The successive differences go to 0, but we saw here just before this, we saw that Cauchy sequences are necessarily bounded. So of course, root n, this is not bounded. Similarly, log n, this is also not bounded, but you can check here xn plus 1 minus xn in modulus. So it is log n plus 1 minus log n. If you use property of logarithm, it is log of 1 plus 1 by n. Okay. So this goes to 0 as, so because log 1 is 0. So 1 by n goes to 0. So 1 plus 1 by n goes to 1 and so on. Okay. So each of these cases, their successive differences go to 0, but they are not Cauchy because both of them, they are not bounded. That is one of the things. Cauchy sequences have to be bounded. Okay. So again, you may wonder, what about, okay, if I replace n plus 2, xn plus 2 minus xn, is that working? Okay, so I will leave it to you. So it's not enough to just require successive differences to go to 0. You need all of them. They all need to be close to each other after some stage. Okay, so that's a bit different than requiring this one. Okay. Okay, so now I state, what the main thing is. So again, so you see in all these theorems that we want to ask the reverse question. If you take a Cauchy sequence, is it necessarily convergent? So this is the theorem. So let xn be. So just to highlight that we are working in real numbers, so I'll say it's a real Cauchy sequence. Then xn converges. So this is the answer that we already saw, that every convergent sequence is Cauchy. If you're in the real line, then every Cauchy is also convergent. Okay. Okay. So there is a special thing at work here. So how does one get to the limit? Okay. So if we say that it converges, what could be a candidate for this this limit? Okay. So let us give the proof. It is a standard proof. There is no. I'm not giving any novel idea here. Okay. So if xn is a Cauchy sequence, we saw that. So we have seen that Cauchy implies bounded. So this sequence is a bounded sequence. So the sequence xn is bounded. But we have seen the Bolzano-Weierstrass theorem, right? That if you have a bounded sequence by Bolzano-Weierstrass, there exists a subsequence, let's say xnj, which converges. Is that okay so far? Yeah, sometimes I'm not able to hear. Maybe it's on my side.
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay. So we have seen the Cauchy implies bounded. So if you have a bounded sequence, you can extract a convergent subsequence. So from here, if at all this theorem is true, we are saying you take a real Cauchy sequence, it has to converge. If at all it should converge, then we have a candidate, because we know that some subsequence converges. If we know that any sequence, if it converges, then every subsequence converges to the same limit, right? So that means somehow we have to show that this xn converges to x, which is the limit of xnj. Okay. So claim actually that xn converges to x. So this is very special for a Cauchy sequence. So we said that We started with the Cauchy sequence. There was one convergent subsequence. Under these conditions, the whole sequence converges to X. If it is not Cauchy, then it is obviously not true, right? Can you give me quickly an example? Suppose this is not, you didn't start with the Cauchy sequence. Can you give me an example where this is not true? Sorry?
We can take the sequence.
Sir, you please repeat the question. You stuck in between. I couldn't hear the question.
Yeah, so I'm saying here, this is a special property of Cauchy sequence. It's not this fact that we said one subsequence converges to X. Now my claim is, therefore, I'm going to prove that the whole sequence itself converges to X. This only is true under special circumstance. That is, for instance, if Xn is Cauchy. So can you give me an example where some subsequence converges, but not the whole sequence?
-1 power n.
Yeah, -1 power n, for instance. Okay, unless you have
yes.
Yeah, Cauchy is not true. Okay, so how does one show this? Xn going to X, the same limit, that same limit as the subsequence. Okay, so okay, so let us prove it. Again, the main tool we have is triangle inequality. Okay, so what do we know? We know Xnj goes to X, right? So let us say I have to show, let epsilon be given. I have to show that mod Xn minus X is less than epsilon for large enough n. Okay, so let epsilon be given. Then, since the subsequence Xnj goes to X, there exists, I don't know, let's say J1, a natural number J1, such that modulus Xnj minus X less than epsilon by 2. This is for J bigger than equal to J1, right? So now I've given epsilon, my error is epsilon by 2. If you give me an error of epsilon by 2, I can find a large enough J1 so that this happens, right? Now for the same epsilon, Xn, since Xn is Cauchy, we have that there exists, let's call it number J2, such that modulus of Xn minus Xm less than epsilon by 2 for all n and m bigger than equal to J2. Okay, so we had this one and we have this one. So now somehow we have to clever application of triangle inequality. So if you can't apply just directly, so but yeah, so how does one finish? So maybe we can say, let I use J1 and J2. Yeah, so maybe let's say let K capital, or let's say yeah, maybe K. Let K be okay. So you take K maximum of J1 and J2. So maybe here let me just call it J maybe.
So, hello.
Yes.
So in first one, Nj is greater than equal to J1, I think. No? In the
Nj
first
is?
one. Nj.
Yeah.
Nj is greater than equal to J1.
No, Nj is the subsequence, right? So if so the subsequence is indexed by N1, N2, N3. So J is the index for the subsequence, right?
Okay.
Yeah. Okay, so let capital J be maximum of J1, J2. So you just take fix.
But we know that Nj is greater than J by definition.
Yeah.
Construction. Nj is greater than J.
Yeah, exactly. So we can take any take fix an let's say maybe n which is bigger than, oops, sorry, this is n sub this index j. You take the maximum of j1, j2 and just fix something which is bigger than this n capital J. Remember, for subsequences, nj is always bigger than j, okay, or equal to j. It's okay. Okay. So then now we apply. We want to estimate. Remember, our goal is to estimate xn minus x. We want to show for large enough n, this is less than epsilon, right? So xn minus x, if I apply triangle inequality, this is less than xn minus x capital N, this capital N, okay, plus x capital N minus x. Okay, so my point is, why did we have to choose like this? So that when I apply triangle inequality, I want to make sure that each of these terms is small. So I know that if it's bigger than j1, first term, that xnj minus x is small. Okay. The second one, if bigger than j2, it is small. So I have to make sure that something, so that both of those indices, the index I choose must be bigger than both. Okay. So I have fixed one capital N bigger than nj, which in turn bigger than j. So I have this. Now I claim this is, each of them is at most epsilon by 2. Why is it? So you look at the first one. Let's call this 1. This one, is it less than epsilon by 2? When is it less than epsilon by 2? So this is for, this is less than this. This is for n bigger than equal to capital N. Yeah. Okay. So why is this less than epsilon by 2? Because I just have to check whether this this n, is it bigger than j2? Is it bigger than j2? Yes, right? Because capital N is bigger than j. J is the maximum of j1, j2. So it is bigger than j2. So this is less than epsilon by 2. And this one, xn minus x. So again, xnj, remember n is bigger than nj. So xnj minus x, this is also less than epsilon by 2. So therefore, the second term is also less than epsilon by 2. Okay, so this is equal to epsilon. So here, you don't, this is just like a term that's usually this is auxiliary term that remember that this is what we used. Okay, so we used a special term to for using this triangle inequality, so that both the indices are bigger than j1 and j2. Okay, any questions?
Sir, can you please repeat from that capital N greater than NJ and greater than or equal to capital J?
So this part is okay, that NJ bigger than equal to J is fine.
And yeah, this line of from below, I think from below.
Okay, so I use triangle inequality. So okay, so I'm just claiming. So let's call that first term as 1 and 2. Why is 1 less than epsilon by 2? If n is bigger than equal to capital N. Okay, so I have xn. So capital N is bigger than capital J, but J is bigger than equal to J1 and J2, right? In particular, bigger than J1. So or J2 in fact. Okay, so if it is bigger than J2, then you have, if as long as both indices n and m are bigger than J2, it is less than epsilon by 2. So here you have little n and capital N. Both are bigger than J2. So it is less than epsilon by 2. Similarly here, xn minus x. So why is this? Sorry, I should take. Yeah, maybe let me just, I wrote something here. So, oh yeah, that is fine, right? Yeah, okay. Oh, no, okay, sorry. Yeah, we can just take this x and j. Yeah, sorry. Okay, so I just replaced it there. Is this okay now?
Yes, sir.
Okay, so excuse me. Yeah, so that is the end of Cauchy sequences. So what we did was bounded. You first prove is bounded. From bounded, you use Bolzano-Weierstrass, and then you do this neat trick where you show that some subsequence converges, then the whole sequence converges. Okay, so that is the end of the Cauchy sequence part. So let me just look at my notes, what I wanted to do next. Yeah, so probably I will, I will start with series. I only have another maybe 15-20 minutes or so. So yeah. Okay, so let us go to some concepts in series. Okay, so just this notation, this sigma notation. So let's say that let A and be a real sequence. We say that sigma n goes from 1 to infinity, converges if you look at the when do you say that a series converges?
The sequence of partial sum converges.
Yeah, so if the sequence of partial sums, if let us write this Sn, which is the sum of the partial sum starting from 1 to n. Okay, so if Sn, which is the partial sum of Ak from nth partial sum, if this sequence converges. Okay, so of course when I say converges, I always mean converges to a real number. This is I just write it once, but it is understood. Okay, and we say that if the value, so the value of the limit, if Sn converges to S, then we say we let the value of this series, we say this is S. Okay. Okay, so a series converges if the sequence of its partial sums, you form each partial sum as n goes to infinity. If the partial sum, this sequence converges, then the series converges. That's our definition for series. Okay, so there are a few basic things with series. So let me say a few basic stuff. Okay, so what are some basic properties that we know about series? So so one thing is that let me just write that so if the terms an are non-negative, okay, then the series converges if and only if the sequence of partial sums Sn is bounded. Okay.
They're bounded enough, bounded above is enough, or bounded needed?
Well, I am always saying that they are non-negative, so automatically they are all bounded below, right?
Yes, sir. Okay, bounded above is enough.
Okay, so for non-negative terms, the series sigma an, this converges if and only if Sn is bounded. Why is this? Why? Well, because you see Sn plus 1, what is it? Sn plus 1 is the sum of all the terms up to n plus 1, from 1 to n plus 1. So this is Sn plus an plus 1, right? So you collect all the terms up to n, and then the last one, n plus 1, you write separately. But we know that an, all terms are non-negative. So this can only be, so Sn plus 1 is bigger than equal to Sn always, because an plus 1 is positive or non-negative. So you see that, therefore, this is a increasing, monotone increasing sequence. Therefore, Sn is monotone increase. So we already have seen a monotone increasing sequence converges if it is bounded above. Okay. Anyway, since anyway this is bounded below by 0, it's okay. Yeah. So this proves both ways actually. So the other way is more easy, because if the series does converge, that means what? That means sequence of partial sums Sn converges. If Sn converges, Sn is obviously bounded. Any convergent sequence is bounded. So the other part is easy. This part, it's also still easy, but there is a small observation that the partial sums form an increasing sequence. That's why if it is bounded, then it will converge. Okay. So this is one example. So if you have a negative, if you have non-negative terms, if you want to check whether series converges or not, even if you don't know the value of the series S, you can still just look at the partial sums and say if they're bounded, then you're done. It's actually going to converge. Okay. So of course, now I come to the most important series. So this is the most important series. This is the heart of everything. Okay. This is the series. So you fix a number, real number lambda, which is in size, in modulus, it is less than 1. So it has to lie between -1 and 1. Okay. So let's look at, this is the geometric series. This is, let me write it here, the geometric series. This is at the heart of everything. Okay. So let's look at the series. Okay. So we want to know whether this converges or not. Usually, believe it or not, most of the series, you can only say it converges. You don't actually know the value of the limit. You cannot very easily compute that. Okay. But anyway, so this one is one of the few that you can actually compute. Then what is, so if you look at the partial sum Sn, this will be lambda power 0 plus lambda power 1, blah, 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 all the way up to, say, lambda power n. Okay. So this is 1. Lambda power 0 is 1. Okay. So this is 1 minus lambda to the n plus 1 by 1 minus lambda. Right. So finite geometric series.
So it should be lambda to the power n minus 1.
No, so these are my, this is how I'm defining Sn. Sn is starting at the lowest index, going all the way up to the nth one.
Okay.
Yeah. Okay. So you have, so here, not only do you have an estimate, there is no, it's not better than an estimate. Sn has actual formula. You actually know what Sn looks like. So you can see that since mod lambda is less than 1. Yesterday in the problem session, there was some problem like this. Mod lambda less than 1. Lambda power n plus 1 goes to 0 as n goes to infinity. Right? A power n goes to 0 if a is less than 1. Between 0 and 1, a power n goes to 0. So this is the fact. Okay. Therefore, Sn goes to 1 by 1 minus lambda. So this is the thing. So of course this is okay. It's easy, but it is because I'm just doing it because it's the most important. Okay. So of course this gives us a wide example, right? So you just take any number less than 1 in modulus, then that series you take this power series, so-called power series that converges, geometric series that converges. Okay. Okay, so I will just do the Cauchy criterion. This is again very, very important for series. Cauchy criterion for series. So the series converges if and only if given an epsilon positive, there is a capital N again which depends on epsilon, such that modulus of let's say a k, where you sum from m to n. So this is less than epsilon for m and n bigger than equal to capital. Okay. So this is sometimes okay, so I'll just write it. So you want to say that the series will converge if and only if you take sections, far enough sections of the series. So after some stage, n is this big number. After that, if you sum any number of terms, they have to be less than epsilon in size. Okay. So this is simply Cauchy criterion for the sequence of partial sums. Proof. This is a one-liner. Okay. Series converges if and only if the sequence Sn converges, and the sequence Sn converges, that is if and only if Sn is Cauchy. Right? We have seen that Cauchy sequence in real is exactly those which converge. So if Sn converges, then Sn is Cauchy, and if Sn is Cauchy, then it also converges. Okay. But exactly what is this? Therefore, that is for a given epsilon, there is an m, there is an n which depends on epsilon, such that Sn minus Sm less than epsilon for n and m bigger than equal to n. Right? But what is Sn minus Sm? Remember, Sn is all the terms starting from 1 up to n, and Sm is all the terms similarly 1 to m. Okay. So if you take their difference, then you will be left with, let's say for instance, n is larger, then Sn minus Sm is exactly in modulus. This is exactly modulus of ak m to n. So maybe what did I write here? M. Okay. So let's say n bigger than m bigger than. Okay. So this is okay. So this is exactly, if it is Cauchy, then the difference is less than epsilon, and but the difference of the partial sums is exactly this. You just sum it from m to n. That's it.
Then it should be m plus 1 to n.
Yes. Sorry.
The sum is m plus 1 to n, something like that. Because up to m it
Oh,
will be.
yeah. Okay. Yeah. That's true. Yeah. So maybe we take m plus 1 to n or something. Yeah. Okay. So in particular, this tells us, so this is a simple corollary, that if the series converges, then the individual terms mod an, so the in size they go to 0. Okay. If the modulus of the sum of bunch of terms go to 0, then surely one of them, if you just take one term in that also goes to 0, right? So just take whatever, m equal to n or something, Sn m equal to n minus 1 if you like. Okay.
Excuse me, sir.
Yeah.
So that sum, I mean the tail from m plus 1 to n,
yeah,
does that imply that entire tail, like m plus 1 to infinity, that sum is also less than epsilon? Or I mean, so we can make that thing less than epsilon for some threshold
yeah, for
number.
large enough. So that's what, if you take if you fix, say, take n, this capital N, then from n to infinity onwards. So if it holds for everything, then right? Yeah.
Okay. Okay.
So what we have seen so far is that for non-negative terms, convergence happens only if the partial sums are bounded. Then we know that geometric series we can explicitly compute as long as mod lambda less than 1. We have an explicit formula not only for the partial sums but also for the limit. The series converges to 1 by 1 minus lambda. And we have this Cauchy criterion. Cauchy criterion means that the series will converge if and only if this so-called tail, in some sense, this is the tail of the series, that can be made arbitrarily small. Okay. So in particular, if a series converges, then this can happen only if the individual terms go to 0. So just one simple example. We saw an example of a convergent series, but if mod lambda bigger than equal to 1, then the corresponding geometric series, lambda power n, this series, if whenever something does not converge, we say it diverges. So this diverges because the terms lambda power n is the nth term. This does not go to 0 because it is bigger than 1. So any number in modulus, if it is bigger than 1 or equal to 1, then if you take power, it will always stay in size bigger than 1. So we have an example of a non-convergent series, a divergent series. Okay. Okay. So
we are not able to see the last line, sir. This last line.
This is the last line.
Yes, sir. Just makes upper side because last line is not readable.
You can you see this? I don't know. This is the last line. The lambda power n diverges. That is the last line.
It is not showing, sir. I think
it's not showing.
You need to scroll up, I think.
Yeah.
Last slide.
Is this okay?
Or it goes to next page.
No, that's next page, sir. It was visible to us. The previous page was entirely visible to us.
Yeah, so I don't know. I am, at least in my screen, I'm able to see it.
Okay.
I don't know. Is it
I
visible?
can see from my side.
Okay. Is it visible now or no? Whoever raised this point.
It's fine, sir. Okay.
Okay, fine. Let's continue. So we have seen example of a series which converges and so on. Then we have seen one example of a divergent series. So maybe just do another example. So more than series convergent of a series, if the series is convergent or divergent. I mean, all these rules, ratio test, this and that, whatever, those are okay. But you should try to really focus on why hard estimates. Okay, that is more important than knowing some rules. Better just know the basic thing, which is geometric series and comparison test. These are the main things. Okay. Rest of it is just follow up of this. Everything depends on this. Okay. So anyway, yeah. So let us prove directly. Maybe we have like 4 or 5 minutes, but let us prove that. So we have seen that if, in particular, if some if a series has terms which don't go to 0, then it cannot converge. Okay. So yeah, let us look at this. Yeah, everyone will know 1 by n, the series 1 by n. n from 1 to infinity, this diverges. But why does it diverge? Okay, so you see that these are non-negative terms, right? So non-negative terms, we have seen already. Non-negative terms, if you take, the series will converge if and only if the partial sum sequence is bounded. So we are going to show that why this diverges. Certain partial sum along a subsequence, this partial sum is not going to be bounded. Okay, so why? So let's look at a few ones. Okay, so let's look at maybe S. Okay, we start with maybe S2. S2 is 1 plus 1/2. Okay, that is okay.
It's partial sum, not a Cauchy.
Sorry?
It's partial sum, not a Cauchy.
Partial sum, not
Cauchy.
Okay.
It's partial sum is not a Cauchy sequence.
Okay, it's not a Cauchy sequence. How does one how does one show? Is it not a Cauchy? How does one show that?
For xm minus xn, for m equal to n, xm minus xn mod greater than equal to half.
Sorry, say it again. Sn minus
xm minus xn.
Okay, xn minus
xm mod.
Okay.
Greater than equal to half.
Greater than equal to
for m equal to n.
For m equal to 2n.
2n. Yes.
Okay.
So it is not Cauchy, not convergent, and also not bounded.
And also not bounded. What do you mean? Where is boundedness coming here? Which you mean the sequence of partial sums that is not bounded?
Sequence of partial sums.
Okay, yeah. So that is also one way. Yeah. So why does this? So you said that if m is 2n, so let's follow that one idea which was given. If you look at the modulus s2n minus sn, the claim was it is bigger than equal to half. Why is this? If you take s2n minus sn, so maybe let me just erase this so that we have more space. We can try this out. So what is s2n minus sn? So that means it will start at where? 1 by n plus 1.
Yes, plus 1 by n plus 2.
Yeah, and all the way to 1 by 2n. Okay.
Yes.
Okay.
Greater than or equal to?
Yes.
Greater than or equal to 2n minus n by 2n.
Okay. Yeah. So each term, I think it was Praful Das. So each term, this is definitely bigger than 1 by 2n, 1 by 2n, and so on, right?
Yes, yes, sir.
1 by 2n. So denominator, the smaller one,
sir,
is larger. Okay. So 1 by n plus 1. Okay. So how many terms are there like this?
2n minus n.
N terms.
Yes.
There are n terms.
N terms, right? 1, 2.
Yes, yes.
So
N
this you can
terms.
write n plus 2n as n plus n. So there are n terms. Okay.
Yes, yes.
So n by 2n.
2n
is
equal to half.
Yeah. So then yeah. So what does this mean? So this is one way to do it. So therefore this cannot this sequence.
So not convergent.
Yeah. Sn cannot be Cauchy. Is not Cauchy. Right? Because no matter so if you take along s2n minus sn, then it is at least half.
Sir.
Okay. So this is one way to prove it. Okay. So hence not convergent. Okay. So that is we have seen two examples now. One is this 1 by n. The other one is the geometric series with size bigger than 1. Okay. So yeah, so maybe I will stop with this following theorem. This is again one of the most important one. So comparison test. Okay. So I will stop with this. So comparison test. Suppose you have a a sequence of non-negative terms that converges B such that okay, suppose you have a sequence of non-negative terms so that the series sigma Bn converges. If An is a sequence such that mod An less than equal to Bn for all n, it's okay. You can leave out a finite number of n. That is fine. You can say for all n, maybe for not for all n, but except for all n starting from some stage. That's fine. Then the series sigma An also converges. Okay. So this is the comparison test. So I will just prove this, and then we will continue next class. Maybe do the first 10 minutes or so, and then maybe continue to see. But what is the quick proof of this? That if this happens, we are starting with a sequence of non-negative terms so that the series converges Bn. Therefore, we want to conclude that the series An also converges. So what is it? So remember, we have Cauchy criteria for series, right? Cauchy criteria says that if only if in modulus this some finite sections for large enough sections, those must be small. Okay, so let epsilon be given. Since these are non-negative, since this converges, there is an n such that, let's say bk, k from m to n in modulus is well, modulus does not matter here because they are non-negative anyway, less than epsilon for n and m bigger than m, bigger than equal to n. Okay, so this is Cauchy criteria applied to the sequence, the series of bk. We know that converges, therefore Cauchy criteria applies. Okay, but now if you look at mod of this sum ak, where k goes from m to n. So if you look at mod of this by triangle inequality, this is definitely less than equal to mod ak from index k going from m to n. But you see our basic hypothesis, mod an less than equal to bn for all n. So therefore mod ak, each of them, it is less than equal to bk. So if you sum them up, it is less than bk from m to n. And by the previous line, we have that this is less than epsilon. Okay, but what is this? This is Cauchy criteria for the series ak. This is exactly Cauchy criteria. Cauchy criterion for. So this is again for m bigger than n or n, sorry, n bigger than m, bigger than equal to capital. So this is exactly Cauchy criteria for the series. Okay, hence this series converges. So comparison test is following directly from Cauchy criteria. So once you have something dominates, then you just estimate by triangle inequality. You see that you can also make the tail of the required series small. Okay, so this is the main thing. So next class we will do few examples. How we'll see how the geometric series and comparison are basically from here everything follows. All the other things that you have, these are the two main things. Okay, so I will stop here. If you have some questions, you can feel free to ask. Any questions?
No, sir.
Okay.
Hello.
Hello, yes, Sunanda, are you asking something?
Yeah, I have a doubt, but am I audible?
Yeah, I can hear you. Yeah. What is your doubt? Yes. You can't. Sorry, someone said you have a doubt, right? So, what was your question?
Yeah, Sunanda, you are not audible now. Are you saying something? We cannot hear you.
No, sorry, maybe some mic issue.
Yeah, now we can hear.
Okay, the thing is, sir, if I have a general question, if you go to that slide where you have given the example of that xn plus 1 minus xn, that mod that tends to 0.
Yeah.
So there actually we have come up with an I first like you told us to guess whether it is true and then why not. So triangular inequality, that is okay. So because I want to know, suppose I'm going to teach this to a student. So
Okay.
if I want them to think like what will be the example which will satisfy this, how that will come to someone's mind that this is the root n is an example. So
okay, yeah. So okay, so I can talk about log n better because, for instance, we have seen that 1 by n, this series 1 by n diverges, right?
Yes.
So actually, if you look at, if you say, so actually, so maybe this was the reason why I took, so if suppose xn was 1 plus 1 by 2 plus 1 by n, okay? So if you take xn to be the partial sum of this harmonic series, what is xn plus 1 minus xn?
xn plus 1 minus xn.
Yeah.
Yes, I'll just get 1 by n plus 1.
So that goes to 0, right? So
Agree.
yeah, but the fact is, so how does, we have seen that this series diverges, but if it diverges, how does it behave? One can actually show by maybe by integral test or something, but,
No, but we are here in the series, no? Sorry, in the
yeah,
sequence.
yeah. Well, series sequence, I mean, when we say talk about series, the part that determines whether a series converges or not is looking at the sequence of partial sums, right?
No, by the time I would have not taught them what is series also, now how they will know what is series. So from the sequence only they will think, like suppose students have to think what is the example.
Yeah, no, that's what I'm trying to say, that yeah, so how does one get, how does one sum enough things to get, so that you have to add a bunch of things, but they need not be small. Okay, so this is the point, that yeah, how does one come up with this? One should think about small, the successive differences is small, but when you take the whole thing, they are not so small, they need to be somewhat big. So this is the example. Okay. Yeah.
Okay, sir.
Maybe there are other examples, but I'm just yeah, so this is
So everywhere that is the problem I face, like okay, example we can see, and then but when we ask them to think, so we want them to think, right?
Yes.
So that is the place how to, or which approach, which direction they should think to get that example. That is my question actually. So
yeah, see, if
thank
they,
you.
I mean, anytime, how does one come with examples or counter examples? Like with everything else, it is practice. You solve several problems, you do several techniques, then you already pick up some, it is building your intuition also takes time, right? Someone was saying, it takes time to understand, but building your intuition also takes time. How does it come? Same practice. You solve various problems, you understand the basic examples, then hopefully there will be a time when you can come up with your own example or counter example. Okay.
Yeah, sir. Yeah, that's true.
Okay. Any other questions?
Sir, I have one point. Sir, actually taking xn plus 1 minus xn modulus, first we take this goes to 0, then we try to verify whether this is Cauchy or not.
Okay. Yeah, so, that's what, yeah.
So we take an example, suppose xn, arbitrarily example, we find xn plus 1 minus xn mod, whether it tends to 0 or not. If it tends to 0, then we first tell the students verify whether this is Cauchy or not.
Okay. Yeah, that's what we have. That's what we have asked here, right? If
my point is how to motivate the students.
How to motivate the students?
So given, madam said that given an example, how in one's mind this example arises. So first, the point is that xn plus 1 minus xn modulus tends to 0. So we choose a sequence. First thing, the xn plus 1 minus xn modulus tends to 0. Then we verify or tell the students whether this is Cauchy or not, we verify it.
Okay.
So this is my point.
Yeah, but the point, they have to come up with the example, right? I mean, she asked, how does one come up with an example or a counter example? I mean, I cannot answer for how someone else can come up, but yeah, so my suggestion would be this, that you comes with practice. You try various problems and then you see various techniques, then you can probably figure out how does one make something not work. Okay, so that is the thing. Okay. All right, so maybe I will stop here if there are no more questions. And yeah, so I'm going a bit slower than I wanted to, but that is okay. I think as long as things are clear with people, and it's fine. So maybe, yeah, let's continue tomorrow, where I will do a little bit more of series, maybe half the lecture on series, and see if I can start continuity and do a little bit of that. Okay.
Yeah, so I think we can end the session today here. We will meet tomorrow. I just want to ask something like, so when we teach sequences to, let's say, undergraduate students, is it a good idea to also give examples of sequences which looks like, partial sums, like in sequence chapter itself?
Yeah, I think because anyway you're going to talk about that, so why not introduce it so that they are already aware of this, familiar with this this particular sequence, right? Why not?
Correct. Yeah. So I think that also, what Sunanda was asking, it might have some partial answer. I mean, usually when we do sequences, I think the only sequences we do is of the form mostly, like 1 by n square, sine of something, like with just one term, but not summation of certain number of, summation of n terms. So I think if we do that in sequence itself, it might help the students. I feel so.
Yeah, definitely. Yeah, I mean, yeah, why not? If you're going to
say something. Hello.
Yeah. Yes, ma'am.
So this is example in book. This xn is equal to 1 plus 1 by 2 plus 1 by 3 up to 1 by n. This is example in sequence in this book, Sherbert and Bartle. Yeah, in our book, this example is there in sequence itself. Xn is equal to 1 plus 1 by 2 up to 1 by n.
Correct. Yes, ma'am.
This is example of sequence, not the partial sum, sir. Like here, we are not taking the partial sum. This is a sequence itself. 1 plus 1 by 2 up to 1 by n.
Correct. Yes. Yeah. I just meant sequence which looks like partial sums of,
But this is not the partial sum of 1 by n. This is actually the sequence.
Okay.
Yeah.
Okay. So
yeah, I think
we'll see you tomorrow.
Yeah. Yes. Thank you, Kosuhik.